Welcome back. This is 6.2.53. We're going to use FV2, the MATLAB toolbox, to examine this example. We have converted the z transform of the difference equation to this yz minus 0.5 z minus 1 yz. And we are going to move the yz's on one side so that we can now express this as h of z, which is yz over x of z, and it is simply 1 over 1 minus 0.5 z minus 1. Now this is the form that we want in the negative powers of z. For immediately we can then write b's and a's. B's is the coefficient of the numerator and a is the coefficient of the denominator in negative powers of z, from z to the power 0, 0 to the power minus 1, and so on. So the first one represents by 1 times z to the power 0. This 1 and minus 0.5 represents the 1 here, which is 1 times z to the power 0, and 0.5 to the power z minus 1 is here. The minus came from this minus. Once we have the b's and a's, we can plug in into FV2s. The b's are 1 in this example, and 1 comma minus 0.5 in this example. We then compare. We'll then take a look at the magnitude and phase response. The horizontal axis is the frequency with respect to pi, and this axis is for magnitude. This is not log magnitude, so you have to change it to magnitude, and this is phase in radians. The blue represents the magnitude and the red represents the phase. In our example previously, we are interested in 0.1 pi, so we go and look at 0.1 pi and look up to these two values. So the magnitude response is at 0.1 pi, it is 1.826. At 0.1 pi, the phase is minus 0.287. Let's compare this with our previous example. In page 34, this was the question that has generated the difference equation. This is the frequency response. So this is at 0.1 pi, the magnitude is 1.82, which is correct, and the phase is minus 0.286. Let's go back. So this is the magnitude and phase. So if you are interested in plotting the frequency, the impulse response, you can hit the button on the impulse and you generate the impulse response. Notice that this is the IIR because it goes to infinity, although it looks like 0, but it's just very small. And you can also generate the poles and 0. Shows that the pole is inside the unit circle, therefore the system is stable. Now, to recap, you go to appendix 6.2 to make sure that you understand how to convert from a difference equation to a z transform version of it to get the transfer function, as well as to identify the coefficients in negative powers of z to get the b's and a's. So in this example, we have went from this equation to here to h of z. The coefficients are in powers of z minus 1, so we just look at the coefficients 2 and 3, so b's are 2 and 3. The a's is 1 and 0.2. And why is this so? Please look at this expression of what is MATLAB expecting of h of z, which is the negative powers of z arranging from z to the power 0, z to the power minus 1, and so on, for both numerator and denominator. We can then use filter BA or FV2 BA to get our FV2 and analyzing our filter. This is the DF1 representation of this difference equation. Don't fall into the trap. This is yn plus 0.2 yn minus 1. This will go to the right hand side, becomes minus 0.2 y minus 1. So look at the coefficients properly. It is minus 0.2 yn minus 1 and sum, which is this expression over here. Alright, then the rest you can figure it out. You just hit the button of this for magnitude. Remember that magnitude will sometimes give you the axis in a log scale. You have to change it into magnitude. This is phase. This is the magnitude and phase together. This is the impulse response. This is the pole 0 diagram. So this is all you need for FV2. Right, thank you.